We talked previously about regularized empirical risk minimization, in which we seek to minimize a surrogate loss function plus a regularization term. The loss helps us fit the data, while the regularization term helps to mitigate overfitting, and lambda governs the trade-off. In this video, we'll talk about solving this optimization problem using gradient-based optimization. Our starting point is gradient descent. It's an algorithm for minimizing a function f with respect to some parameters theta by taking steps in proportion to the negative of the gradient. Eta is the step size, also called the learning rate, which can depend on the step number t. With certain conditions on the step size and the objective function f, this simple algorithm will converge to a local minimum. However, in our case, f is a sum over training examples. So every time we update the parameters, we need to iterate through the entire training set. The solution is to use stochastic gradient descent, or SGD, which is very similar to gradient descent, except it makes updates much more frequently, using the gradient calculated on a small subset of the training data, usually a mini batch of size 100 or so. The term stochastic here refers to this being a stochastic approximation to gradient descent. There's no random noise added to the gradients or anything like that. SGD is applicable when the objective function is a sum, as it is with empirical risk minimization. It converges much faster than gradient descent and has some similar guarantees under certain conditions. As SGD is widely used in machine learning, many ways have been developed for choosing and adapting step sizes dynamically for individual parameters. However, what if our loss function is not differentiable? The perceptron and hinge losses are not differentiable due to the max operations. Fortunately, they are subdifferentiable, so we can compute subgradients and use stochastic subgradient descent. A subderivative is a generalization of a derivative for convex functions that may not be differentiable. While the derivative is the slope of the line tangent to the function at a point, a subderivative is the slope of a line that touches the function at a point and is either touching or below the function everywhere else. There can be multiple subderivatives at a point. Given the piecewise linear function shown in blue, these two red lines are subderivatives at the point x0, along with all other lines that lie under the function and pass through the point x0 f of x0. The set is called the subdifferential, and a convex function is differentiable at a point if and only if the subdifferential at that point contains only the derivative. Stochastic subgradient descent is like SGD, except we replace gradients with subgradients, and it has similar theoretical properties. How do we compute subgradients? Well, at points of differentiability, just use your standard rules for calculating gradients. At points of non-differentiability, when there is a set of subgradients, just find a single subgradient. For stochastic subgradient descent, any subgradient in the subdifferential will work. Let's look at an example, the absolute value function, which we can write as the max of two functions, x and negative x. When x is strictly positive or strictly negative, the function is differentiable, so the subderivative is a set containing only the derivative. But the point x equals 0 is a point of non-differentiability. In this case, we can see by inspection that any line that contains the point 0, 0 and has slope between -1 and 1 is a subderivative. There's a useful rule to get a subgradient when working with a max of convex functions. Choose a function that achieves the max value at that point, and then choose any of its subgradients at that point. For example, at the point x equals 0, both functions in the max achieve the max value of 0, so we can choose either of them and return its subderivative at the point. Now let's work out the subgradients for our loss functions for linear models. First, let's write the perceptron loss using our linear model from earlier in the course. This loss is not differentiable due to the max, but it is subdifferentiable. Let's compute the partial derivative of the loss with respect to a single feature weight wj. The first term is differentiable, so we get negative fj for that term. The second term is not differentiable, so we have to compute a subderivative for it. To find a subgradient of a max of functions, we find a subgradient of a function that achieves the max. In this case, the function computed for the label y prime with maximum score. We already have notation for that, it's just the output of our classify function. This is now differentiable, and we can use usual differentiation rules to find a subgradient, which gives us fj applied to x and the max scoring label. Putting things together, the subgradient for a single parameter wj is the difference in the feature values between the gold standard y and the highest scoring y under the model. We can then work out the parameter update rule in stochastic subgradient descent, which will apply to every weight wj. This update has an intuitive form for the sparse features we've been talking about. If a feature appears in the gold standard but not in the predicted label, its weight will get larger. If the feature is in our predicted label but not in the gold standard, the weight will get smaller. In practice, we typically use a step size or learning rate eta, which is multiplied by the subgradient in the update. This is tuned for the task and is typically something small like 0.01. Now let's see how the update rule changes when we use regularization. Here we have the loss plus an L2 regularization term with strength lambda. This regularizer is differentiable, so we can compute its derivative with respect to wj, which then appears as another term in the update rule. Assuming small non-negative values for eta and lambda, this extra term causes the resulting weight to be a bit closer to 0. So sometimes this use of L2 regularization is called weight decay. Now how about for hinge loss? Recall that hinge loss differs by the inclusion of the cost function in the maximization. The subgradient is similar to that for the perceptron loss, but there is a difference due to the presence of the cost function. Now, when finding the subgradient of the max, we can't just use the classify function anymore, because the max is computed over the score plus the cost. So we define this new function that I'm calling cost classify, which returns the label that maximizes score plus cost. Unlike classify, cost classify requires the gold standard label y as one of its inputs, because that's needed for computing the cost function. This is a new inference problem that is called cost-augmented inference or cost-augmented decoding.